Okay, welcome to this video on resonance structures. And the example we are doing is H2CnOH. And the method we create resonance structures is by electron pushing. We can either break bonds to gain lone pairs on an atom, or we can move lone pairs off an atom to create bonds. And when we do this, we'll cause differences in charges. And it will make a lot more sense once I complete this example. Okay, so we have our atoms already laid out, but we need to know how many bonds our molecule should contain. So this is where this equation comes in. The number of bonds equals the demand minus the supply all over 2. So what is our demand? Our demand is to make sure every atom has either an octet for like carbon, nitrogen, oxygen, but hydrogen is a special case where it likes to have 2. It's the duet rule, so it's like helium. So this likes to have 2, this likes to have 2, this likes to have 8 in the outer shell, so they're like neon. If you add all those up, that should be 30. Let me clean this up first. Minus the supply, which is how many valence electrons each atom can actually contribute. And we find this out by looking at the periodic table. So hydrogen is in group 1, so they each contribute 1. Carbon is in group 14, so they contribute 4 electrons. Nitrogen is in group 15, 5. Oxygen 16, 6. Add all those up, that should be 18. Let me clean it up first. So that's 18. Divide that by 2. So it's 12 divided by 2, which is 6. Okay, so this molecule should contain 6 bonds. So let's get this pencil out. First, always connect your hydrogens with single bonds because they follow the duet rule and they can only have 2 electrons to be like helium. So now we have 1, 2, 3. 6 minus 3, we have 3 bonds left. So let's connect our atom, our molecule, finish it off. And where do we place our last bond? Well, we gotta place it between the carbon and nitrogen, or we can place it between the nitrogen and oxygen. So let's do this first. Okay, now what we need to do is fill in our remaining electrons to make octets. So we have 2 there, 2 there, and 2 there. So 2, 4, 6, 8, 10, 12, 14, 16, 18, which checks off with our supply. So that's good. Now we need to figure out what their charges are by using this equation. Formal charge equals valence electrons minus lone electrons plus number of bonds. So let's just do hydrogen to get out of the way. Hydrogen has 1 valence electron minus the lone electrons, which has 0. So it's 0 plus number of bonds. It makes a single bond. So it's 1 minus 1, and that equals 0. We can see each hydrogen only has a single bond, so we can say they're all 0, has a 0 formal charge. So let's go back here. Let's check out this carbon right here. So carbon is in group 14, so it has 4 valence, minus the lone electrons, it has 1, 2 lone electrons, plus the number of bonds, it has 1, 2, 3, so it's 4 minus 5, which is negative 1. So this carbon has a negative charge. So let me clean this up. Negative charge. Okay. Now let's check the nitrogen. Nitrogen is in group 15, so it has 5 valence, minus the lone electrons, which is 1, 2, plus the number of bonds, 1, 2, 3, a single and a double, so that's 1 plus 2, which is 3. So we have 5 minus 5, and that's 0. So this nitrogen does not have a formal charge, so moving on. You could automatically write plus right here because we know our molecule is neutral, so if we have a negative, we have to have a positive somewhere, and that's our last atom. But I'll show you the formal charge just in case. Oxygen is in group 16, so that's 6 valence, minus the lone electrons, which is 1, 2 lone electrons, plus the number of bonds as 1, 2, 3, a single and a double. So that equals 6 minus 5, which is a positive 1, and so it does have a positive charge. So that makes sense. So that is one of our structures, one of our Lewis structures. So now we're going to create our resonance structure. Okay, now I'm going to redraw this structure over here so I can show you what I'm doing to create a resonance structure so it doesn't get really confusing. So let's redraw it. We have a single bond with the carbon and the hydrogen, a single bond here, we have a double bond here, and then we have a single bond. Now I'm using these as our electrons because they look a lot neater, these little periods right here. So there's a lone pair right here, there's a lone pair down here, and we have a lone pair over here. Keep in mind we also have our charges. So we have this and this. Now what we want to do to create our resonance structure, we want to go from a region where we have a negative charge to a region where we have the positive charge. So let's do that. Whoops, let me get that right there. Okay, so what can we do? We can break a bond. Not in this case, because we already have 1, 2, 3. If we would break a bond, we would be destroying the molecule. It wouldn't work. So we can now try moving lone pairs. So we could do that. We have a lone pair right here. So we could put it right here and make a double bond. Okay, let's try that out. So now we have a double bond. Good. So keep in mind, anytime where we break a bond or we move lone pairs, we're also moving this charge. So the charge is over here now. Okay, how many electrons are on this nitrogen? We have 2, 4, 6, 8, 10. Well, we can't do that, so we need to break a bond. So let's do that. Let's break this bond right here, and we'll put it down here. So let me clean that up. We will add those as electrons so it looks neater. So now we have these electrons over here. Keep in mind, this charge has to keep moving. So now it's over here. Oh, would you look at that? We have a positive and a negative right beside each other. So what's 1 plus a negative 1? Well, that's simply 0. They cancel each other out. Okay, so which one is the better structure? Well, first we look at who has the most octets. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Oh, that has octet. 2, 4, 6, 8. Yep. 2, 4, 6, 8. Yep. 2, 4, 6, 8. Yep. Okay. Well, that's all well. So, are they equal? No, not in this case. So, what's the next case? Well, which one has less charge separation? Okay. So, this one doesn't have any formal charges. This one does. So, that's not as good. So, this would be your major resonance contributor. This would be your minor. And if we combined all of the resonances together, we would get a resonance hybrid, and that is what your molecule actually looks like. It's called the resonance hybrid. That looks awful, but that's what it's meant to spell, is resonance hybrid. Okay, the third possibility that was not shown here is if they all had octets, they both have charges, then which would be the better one? The one with the most negative on the most electronegative atom. So oxygen, found here, is more electronegative than nitrogen. So if there was a negative formal charge on an oxygen and there was a negative formal charge on a nitrogen versus each other, this compound would be better. So these are just some rules you can write down. This is the most important when you're determining who's the major resonance contributor. So octet is the best. And this will overrule all of these. Octet is always the best, no matter what. Least separation of charges, and the negative formal charge on the most electronegative atom. So, yep, that's it for this video. I hope to help.